Now the only problem with doing it this way is that when I hit record, it doesn't record the audio. Now I'm wondering if that's because we both switch it on to phone call. Wonder if we leave it on computer audio, whether it would record it or not. Let's try. The biggest reason for switching it off of computer audio is that there's frequently feedback. And I heard the tone that indicated that your microphone was working. Say something. No. Yeah, no, okay, that's all that happened then. Okay, I'm going to leave mine on computer audio and see if that matters. All right. So, you're into this part of calculus. We must be getting close to the end of new material, right? Okay. Okay. I think it's significant to go over the derivation of this formula, solving this differential equation. Okay, so let me do this. I have a little bit of room to write. Now we've got, hold on. Solving this will come up frequently, even though you only really need to solve it once for these kind of problems, because once you've solved it, then you know what the final equation looks like. How do you solve that differential equation? Do you know? No, what you want to do is separate the variables. Excuse me, hold on a second. I didn't write this from the start, and I meant to. What we know is that the rate of change is equal to the amount that's there, okay? It's proportional to the amount that's there. Whenever you have the rate of change of something with time is directly proportional to the amount that is there at any point in time, this is basically the equation you have. And if you try to solve this differential equation, you do it by a technique called separation of variables. Okay? Solving differential equations is a bit like solving integrals. You've probably already been taught 4 or 5 techniques for solving integrals, or at least a couple: integrals by parts, integrals by, in other words, you don't have a product rule, but you have all these techniques for solving integrals. It's much harder to solve integrals than it is to solve derivatives. Well, differential equations are quite similar. And the most basic technique for solving a differential equation is to separate the variables. Well, I want to get all my n's on one side, all my t's on another. Okay? So if I multiply both sides by dt, I get this. And then if I divide both sides by n, I get that. Okay? With me? Now I'm going to integrate both sides. What's the left side become? What's the right side become? Speak just a little louder. I'm having a little bit of hard time hearing you, Catherine. No, k is a constant. So I could actually pull that k out of the integral sign. What's the integral of dt? T. In other words, it's basically what they're saying is when I take the integral of 1 dt, that's equal to t plus c. Take the derivative of t plus c and you get 1. Okay? So, the integral of k dt is going to be kt plus c. Now, the next step is the tricky one. How do you go from here? And remember what I'm trying to solve for. I'm trying to solve for n. Yes, to e. Now, this is a little tricky. What's the left side become? Good. That's what we're trying to solve for. What's the right side become? Well, it's e to the kt plus c, but I can split that up. What do you do when you're adding exponents? Exactly. In other words, if I started with the bottom, it would turn into the top, right? In other words, same base, different exponents, you add the exponents. Well, this is where I start with the exponents being added and I turn it in to multiplication. And the advantage of that is a number to an arbitrary constant. So I can let e to the c be equal to c. And what that causes is the c to be multiplied. And I'm going to put it in front, and you get this. And this is what you always get, whether you have growth or decay. The real world operates on this principle that the rate of change of something is directly proportional to the amount that is there. Doesn't matter whether it's uranium-222 or whether it's bacteria in a petri dish. There are literally millions of things that go on in the real world that follow this equation, all based on that. Whereas every single one of these, you have something whose rate of change, dn dt, is directly proportional to the amount that's there. And this equation always solves to that equation right there. And notice that when you integrate most of the time, you end up with plus c. So the c is an adding thing. Well, when you integrate these equations, the c becomes a multiplier. And that actually has quite an impact on things like slope field. Are you familiar with slope fields? Well, when c is an adder and you have slope fields, a parabola might look like this, because c merely gives you parallel parabolas, no matter what it is, because it's being added. If it's a negative number, it's way down here, okay? But when c is a multiplier, it gives you different kinds of slope fields. If you're looking at an exponential function that might have a slope field like that, and you might say, well, it's going to be like that everywhere, but the moment c turns negative, you have a reflection over the x-axis, and the rest of the slope field looks like this. So it's not uniform entirely up and down the y-axis. So this process where c becomes a multiplier definitely has an impact on the slope field and all of the possible solutions. In other words, each one of those can be a solution depending on what c is. All right, so we know this is the equation we're going to be using on all of these problems. And it's just a question of whether k is positive or negative. If it's decreasing, like radioactive decay, K is going to be negative. If it's increasing, like bacterial growth, K is going to be positive. Now, having said that, I see a lot of this. For decay, and I see this for growth. Which means K is always positive. I don't quite understand why. It seems like this should satisfy every single situation. If you have decay, K would be negative. If you have growth, K is positive. But for some reason, I don't know that it matters, but I've got books that say that is for decay, this is for growth, which means K is always positive. I don't think it matters in terms of solving any of these problems. Let's have a look at some of these problems here. Let's see. All right. Can you read all that? Okay. I'm going to try writing on the sheet of paper. I finally figured out how to get all my pictures vertical. You just got to put them into paint, and then I can rotate them any way I want. Okay. So the answer to B is N equals C E to the KT. After we solve that differential equation, that's what we get. Okay, now they're saying that suppose there are 100 present at a given time and 300 present 5 hours later, use this information to find a particular solution. Well, a particular solution, we have a number for C and we have a number for K. That's what a particular solution has. Instead of knowing C and K are constants, the particular solution will have solved for them. Okay? So, what's an easy way to solve for C? Well, let's look at that part of the sentence. There are 100 present at a given time. So let's say the number present is 100. And let's make that given time the beginning. So T is 0. Notice how that allows you to solve for C. Any number to the 0 power is what? So C equals what? So now we just have to solve for K. In other words, we know this much. Y equals 100 times E to the KT. And the given time, I could have actually used any time, but 0 is very convenient because it allows me to solve for C. Now, 5 hours later, there are 300. So what's the next equation I can write? Remember, Y is the amount that there is. We know C is 100, regardless of how many hours have passed. We've determined what C is. Now notice there's only one variable in that equation, K. E is not a variable. E is a number. Okay, so let's solve for K. How do I do that? What's the first step? Okay, so we have 3 equals E to the 5K. What next? perfect. Whenever you're trying to solve for a variable that's in the exponent, you're going to have to use logs. And natural log is perfect because the right side now becomes what? The left side is natural log of 3, so k is going to be that. So now we know our particular solution. What is it? T. In other words, this solution will allow us to calculate at any t. If you want to know how many bacteria are going to be there 8 hours later, this will tell you. Okay? Now, we have a choice here. We can convert this natural log of 3 divided by 5 into a decimal approximation and use it. But quite frankly, this is the best way to write it. If we're going to do any calculations at all, we would rather use the exact number, which is natural log of 3 divided by 5, and then round it off at the end. But if, in other words, don't approximate until the end of a problem, almost always. Because you get round off error that can get compounded and all kinds of stuff. Okay, so this is our equation. Now, how many will there be 10 hours after the initial time? So it's 100. Yeah, natural log of 3 over 5 times 10. Well, that's actually not too hard to do because I can cross that out, and I get a 2. So I get y equals 100 times e to 2 natural log of 3, right? And that's a number you can get on your calculator. Do you know how to do that on your calculator? It's a little tricky. You got to make sure your parentheses are correct. This natural log of 3 times 2 is the same as natural log of 9, incidentally, because it's the same as natural log of 3 squared. So here, let's make it as simple as we can. 100 e natural log of 9. You see why that's the same? I don't know how up you are in your logs, but that number you can get, actually, that's 900. In other words, I don't need a calculator. E to the natural log of x is x. So there's going to be 900 bacteria after 10 hours. And you can only imagine how much it'll be after 100 hours. It's going to be a lot. It's like the Blob. I don't know if you ever saw the movie The Blob, but okay. So, well, it was this thing that came from outer space, and it just kept growing and growing and growing, consuming people as it grew. So, let's see. We've got our equation. I don't think I need to erase that. Let me erase this. How long did it take for the number of bacteria to double? How do you do that? Actually, I don't think it matters. I think that no matter what you start with, there's a certain amount of time that it takes to double. So, yeah, starting with 100 to get to 200. So I'm going to solve this problem. for t. Again, t is the only variable there. Okay, so what's the next line of that solution? So 2 equals e to the natural log of 3 divided by 5. And make sure that's not the natural log of 3/5. It is different. Now what? Okay, so the natural log of 2 equals natural log of 3 divided by 5 times t. So t equals what? Let's simplify that. It's only one simplification needed of 32, 2 to the 5th, divided by natural log of 3. Can't really simplify that anymore. And in case, it's definitely not subtraction. In case you might have thought, I mean, this is really easy for a student who hasn't had logs in a while to confuse this to natural log of 32 minus 3. It isn't. If I had the natural log of 32 divided by 3, that would equal the natural log of 32 minus the natural log of 3. But if I have the natural log of 32 divided by the natural log, there's no simplification allowed. And you definitely cannot divide. In other words, you can't eliminate the natural log. There's times where you can do that. If I got the natural log of x equals the natural log of y, then I know x equals y. You know, you can kind of look at it like you're dividing both sides by ln. But you cannot, it's not really the natural log multiplied by 32. It's the natural log of 32, which is a specific number. All right, enough with this problem. Let's go to the next one. And let me bring up the next one a little higher in my page here. Warfarin. Very common drug that they give people who have strokes. All right, so that tells you right there the rate that it decreases is proportional to the quantity remaining. So immediately we know what is the equation for this without having to work through all that solving that differential equation. What's it going to be? I guess, yeah. I don't think it matters whether you call that negative k or not. If you call it negative k, then k comes out to be positive. If you call it k, k comes out to be negative. I'm not sure. I guess this tells you immediately that you're looking at decay. It's still a little odd to me that they don't just use k and let you solve for a negative or a positive k. There must be a reason that I have not figured out yet. But anyway, so if we wanted a graph of this, what's it basically going to look like? In other words, we know exponential growth looks like that, right? What's exponential decay look like? When you see, think of it as a transformation of an elementary function. When there is a negative sign in the exponent, what does that cause? The exponential, it's a reflection over the y-axis, right? In other words, e to the negative x is the same as e to the x, only reflected over the y-axis. So instead of looking like it did, it's going to look something like this. That's what exponential decay looks like. Now, we can actually put some numbers on there. I'm going to make one up, 2. The reason I made that up will become apparent here. We know the half-life is 37 hours. Meaning that after you stop administering the drug, 37 hours later, there will be exactly half the amount in the patient's body. So what that means to me is 37 got to be half of 2, 1. With me? And then they're going to ask a question, how many days does it take to reach 25%? Well, that's actually a pretty easy question. Let's answer that immediately. Number D. In other words, we just went to 50%, right? In 37 hours? So how many hours would it take to get to 25% of 2? Yes, exactly. Actually, 37 multiplied by 2. In other words, it's going to keep decreasing, and by hour 74, it will have decreased in half again. Right? In other words, 37 hours after it's administered, you lost 50% of it. It's going to lose another 50% in the next 37 hours. So the only tricky part of that is they say how many days. I don't know why they would do that, but I suppose because it's too easy to answer in hours. But it does highlight the fact that t can be in any time increment you want, depending on what you're dealing with. There are radioactive things that decay in a matter of seconds. So you might make t in seconds. Bacteria grows so fast that you tend to let t be in hours. Some radioactive materials decay so slow that you let t be in years. Doesn't matter. Whatever it's in, then that's what it's in. Now, in this problem here, 37 hours is the half-life, and they ask how many days does it take. Well, shame on them. 74 divided by 24, which is like 3 days and 2 hours. All right, so we've drawn the graph. And all exponential decay is going to look just like that. Now let's go through each question. So we've done this one. Write a differential equation stating the relationship. You've done that one. Solve that differential equation and you get this. Solving it exactly the same way as we solved it before. Find the particular solution using the half-life information given. Okay, well, I think I can do that. Yeah, that allows us to solve for K specifically. In other words, we don't know how much warfarin is in the body, but we do know that 37 hours later, half of it is in the body. Okay, so I can do C over 2. If C is the initial amount in the body, half as much is C divided by 2. So I can write this equation. And I happen to know what the half-life is. 37 hours, not days. Okay? And notice what happens here. The C goes away, divides out, And so now the only thing we have is the k, which we can solve for. So if we do that, we've got 1/2 on the left, and take the natural log of 1/2 equals the natural log of the right, which is minus 37k. So k is going to be the natural log of 0.5, which we know to be a negative number. Natural log of any numbers less than 1 are all negative, divided by negative 37. So indeed, we do come out with a positive k. And go ahead and look that up in your calculator. Tell me what that number is, because rather than writing it as natural log, it's a little bit easier to do the algebra if it's written as a number. As much as I would prefer to see it written as natural log always, in this instance, let's convert it to a number. So it's the natural log of 1/2, or 0.5, divided by minus 37. What do you get? Okay, so there's our k. So now we have y equals, still haven't solved for c yet, minus 0.0187, I'm going to round that off to t. And now we got to solve for c to come up with the particular solution. We need both c and k. I'm not sure how to solve for c, to be honest with you. It didn't look to me like they gave us enough information to solve for c. The half-life lets us solve for k. Let's look at the next question. Maybe that will enlighten us. How many days does it take for the drug level in the body to be reduced to 25% of the original level? Well, that's just solving this. Still doesn't, we don't need C, right? In other words, we don't need C to solve question D. It's going to divide out again. And if we do the math, we already know that it's going to be 74 hours. That's fairly straightforward. I think. I might be a little wrong on that, but I can't imagine it could be anything other than 74 hours. How many days does it take for the... see, all of the questions that they are asking do not depend on you knowing what C is. In other words, the last one is going to be 1/10 C equals C e to the minus 0.0187 t. In all cases, you can solve that for t. I can solve this one for t. In other words, I don't need C. And that's just as well, because I couldn't figure out how to calculate it anyway. The only problem with this whole question is when they say use the information to find a particular solution. Well, this is, I guess you could call that a particular solution. We haven't solved for C. We don't know how to solve for C, but we can still answer all of these questions. I'm just not sure this counts as a particular solution. But it's the only solution I think we can give. We don't have enough information to solve for C. All right, let's look at the next one here. Let me scroll down a little bit. Same thing. As we know, our initial equation is what? I just call it y. Yeah, Y is going to be the amount that's there at any particular point in time. So we know it's C, E. We're dealing with decay, so I'll put a negative sign in front of the K. So that's our equation. You don't always have to go through the solving the differential equation to come up with that. This is just the equation for growth and decay. And yet they continue to ask you to go through that all the time. Okay, so you're right on A. And when you solve B, you will get this differential equation where that will be equal to A. And I think I can fairly safely say that C is the initial amount. In other words, the amount is always going to be the initial amount when time is 0. I don't know that it matters. The top equation is fine, but in looking at the letters you've used down here, you do use A. But we know that's going to lead to a C, and we know that C has to equal A when t is 0. Whenever you plug in 0 for t, it takes this whole e to the minus kt and turns it into 1. So, okay. So, let's see, we've done A and B. The half-life is 1,590 years. So what's that let us solve for? Yeah, how? Let's do it. Give me an equation to write that we can solve. Well, if that's the amount we start with, and after 1,590 years, it's going to be 1/2 of that amount. So let's plug that in. 1/2 a sub 0, the starting amount, equals a sub 0 e to the minus k times 1,590 years. The a sub zeros cancel out, and now you just can solve for k. You're going to end up with the natural log of 0.5 equals 1,590 k. So k is natural log of 0.5 divided by minus 1,590. I bet you that's a really tiny number. What is it? Okay. All right. That's a good start. We know what K is. Now, it says, the sample has a mass of 80 milligrams. Use this information to find the particular solution. And now we're going to be able to solve for C, basically. In other words, we weren't able to solve a particular solution so far. Just like the last problem, we were never able to solve for C. But suppose a sample has a mass of 80 milligrams. Okay, so let's see, what do we've got? We've got the amount at any point in time is equal to the starting amount, say 80, times e to the minus 0.000436 times 1590. Think for a second. Well, we know that would be true, right? In other words, after 1590, whatever you started with is going to go down by half. That's by definition. Suppose a sample has a mass of 80 milligrams. Does that mean C is 160? Seems to me like that's the only way I can interpret that. In other words, if C were 160, then after 1590 years, see, I'm a little confused because is that before the 1590 years passes or after? And I don't think it should matter. I don't think it's still going to allow us to calculate C. So all we know is that whatever C is, every 1590 years it goes down by half. So it becomes half C. So what am I missing here? I suppose one could say 80 equals C times e to the minus 0.000436 t. And if I plug in 1590 for t, c is going to come out to be 160. Now the question is this the particular solution? Maybe it is. In other words, now that's what I think of when I hear particular solution, is that I've solved for C and I've solved for K. And I guarantee you, if you plug in 1590 years, the amount is 80. Because that's how we got K. So we know that whatever that coefficient is in front of E, when T is 1590, A goes to half that number. So if we assume, now does this work for everything? I suppose it does. In other words, if I had 100 milligrams to start with, would this equation work? Part of me wants to say yes, but I'm not positive. Let's plot a graph and see if that is helpful in understanding it. Well, here's what we know. After 1590 years, the amount has gone down by half. So the amount was C, it's now half C. So if I'm graphing it, it looks like this, right? And it's still going to keep decreasing by half every 1590 years. Still don't get how you can solve for C. I don't. For some reason, this does not seem to me like enough information to solve for C. Can't be. Because what if you waited another 1590 years? Your mass would now be 40, right? That wouldn't allow you to solve for C. I don't think. I might be missing something here, but I don't get it. And once again, I don't think we have to solve for C to graph the rest of this thing. I'll bet we don't. Watch, we won't have to. In other words, we're going to go with a particular solution that is this. The amount is equal to some constant times E to the minus that. Okay, so that's our equation. That's our particular solution, as much as I don't really think it is, but I don't know what else to do. And I bet you we can still answer all these questions. So I plotted the graph, and that's a reasonable plot. It would keep on going like this. In other words, it would be a exponential decay. And I don't need to know what C is. All I know is that whatever C is, it goes down by half every 1,590 years. So I've done that. This is time. What's the mass after 1,000 years? Well, the fact that they didn't tell us what the starting mass was means it has to be that 80 milligrams, right? I don't think it could be anything else. Unless I just went back and reread the whole problem and they don't tell you any other starting mass. So this sample mass of 80 milligrams has to be the starting mass. Wow. Okay. So A, So it's not going to go down by half even, is it? So what's going to be left is something greater than 40. So if I solve the problem and start with 80, e to the minus 0.000436 times 1,000, you can come up with a solution. In other words, everything on the right side you can put into your calculator and come up with a number. Go ahead and do it. Let's make sure that it's somewhere between 40 and 80 milligrams. I guess this is going to be about 60. $61.7294. Pretty good guess, actually. Because it's not linear. It's exponential. So, okay, so we were able to answer that question. When will the mass be 30 milligrams? Well, we're going to take that same equation and substitute 30 over there. In other words, when does 80 become 30? Do you know how to solve that for T? I'll bet you can too. So let me see if I can guess on this one. 30 would be a little less than half, so it's got to be a little bit more than 1,590 years. I'm going to guess 1,800 years. It's going to be the natural log of 3/8 divided by negative 0.43. What's that number? $2.281 instead of 1,800. What did I do here? I substituted a. Oh, I didn't. I'm sorry, I didn't do this right. I'm going to divide both sides by 80, so I'll have 3/8 on the left side, And I'm going to take the natural log of both sides, which is going to give me minus 0.00043t equals natural log of 3/8. So it's actually, I made a mistake here. The time is the natural log of 3/8 divided by 0.00043. Okay, that's in the ballpark. That's the advantage of always using the ballpark as a check. In other words, I knew the answer had to be a little bit bigger, or had to be somewhat bigger than 1590. So when you gave me your first answer, that tells me I made a mistake somewhere. It's not in the ballpark. And yeah. Okay. So notice that we didn't need to know what C was on both of those or the above question. So when they ask for a particular solution, that must not necessarily mean you have to know what C is. Because we were not able to calculate C on either of those problems, and yet we were able to answer all the questions. Or else a particular solution allows for C being C. In other words, maybe you don't need a number there. But on the first one, we were able to calculate C and K. Okay, let's see. That's all we have on this? I hope that was helpful. Was it? Good. Yeah, it really requires as much log knowledge as calculus knowledge. You have to remember your log rules. And that's one of the advantages of always using natural log when you're solving. You know, you can have lots of equations. If I tell you that 7, excuse me. If I tell you that 7 equals 2 to the x, solve that. Well, a lot of people are tempted to take the log base 2 of both sides. But you really shouldn't. You should just always use natural log. It's not any longer. It looks like it's a little bit longer, but it isn't. You get natural log of 7 divided by natural log of 2. That's basically the same exact number of steps if I would have taken the log base 2. Because notice if I take log base 2, now I've got log base 2 of 7 divided by log base 2 of something else. But it's why you quickly learn to just always use natural log, because in calculus everything is e to something, and so natural log is by far the best log to take of both sides. But even in just regular algebra, it turns out to be just as efficient as any other log. Natural log is the log of math, so I just always take natural log of both sides. Catherine, you have any other questions? Okay. Well, you said you have a quiz tomorrow? Oh, your last test before you start reviewing for the AP? Oh, you have 2. Okay. What are you getting in calc right now? What is your score? Okay. That's not bad for calc. Maybe you can bring it up a little bit with these last 2 tests. Yeah, when you get ready to take your test semester final, contact me, and when I assume he's going to give you some review material. And when you get that, yeah, set up a session or 2, and I can definitely help you a lot, I think. I can definitely help you there. I'm good at that stuff. Or something that has equilateral triangles on top of it that is a base, like a paperweight. Problems like that, yeah, no, I can definitely help you. a lot. Somebody needs to have a physical tinker toy set that, in other words, if I had a box full of discs of all different kinds of radiuses, then I could show you what that three-dimensional solid would look like. I could just pick out the right discs, put them together, hold it up to you, and it looks just like that horn would look. You know what I'm talking about. And you could do the same thing with washers, and you could do the same thing with cylindrical shells. Now, you haven't been taught cylindrical shells yet, I don't think, but that would be a great tool for getting somebody to visualize what kind of a volume, what's the shape of that volume that you end up with after you rotate a two-dimensional function around the x or the y-axis. So, anyway, I don't have such a thing. I've always wished I did, because I'm not a very good artist, and whenever I go to teach people about it, I can't draw worth a lick. And it's much easier if you can actually picture the shape. So, anyway, good luck on your test tomorrow, and you're welcome. Talk to you next time. Bye-bye.